Hi, I'm Mark Weitzman. Welcome back to Symmetry and Groups in Physics. And I didn't say goodbye at the end of lesson 2 because the battery ran out of my camera. But not much was lost, so I just uploaded it as it was. Today I want to start on get away a little bit from the symmetry transformations and everything that I was discussing last time. We'll come back to that. We only treated some very simple cases last time. They were both what we call abelian groups. And I want to have about 2 lessons on groups just so that I can use the terminology when discussing representations and things like that and not use a word that somebody doesn't know and everything. So I'm going to give what would be like a couple of videos of about 10 minutes each on groups that would normally be covered in months of an undergraduate course. I'm not going to prove anything. I'm just going to state some results. I'm doing it all by memory, so I'm probably going to leave some things out. But let's begin. First of all, what is a group? A group G, Group G is just a set of objects. Let's call them like A, B, C. Could be infinite, could be finite. Mostly we're going to treat finite groups at the start of this course, but eventually we'll go to infinite groups. And then there's a function on the group on the on G cross G. I'm going to use fancy mathematical language here. So this O is meant to be, I'm going to make it smaller, composition and everything. It's just the group operation. And most of the time we're going to leave it out, as I'll explain shortly. But it goes from G cross G to G, which simply means if we take 2 elements like A, then group operation B, we get another thing, let's call it H, and H is in the group. So this is the first property that a group has to have. It has to be closed under the group operation. In mathematics, the group operation could be plus, it could be times, it could be, all kinds of other operations. It's got to satisfy 4 rules. This is the first one. I'm going to call this closure. And we're not going to use this function notation anymore and everything. We're always going to write A composite B. And what we're really going to do is we're just going to leave out the operation. We're just going to go A, B. So the product of 2 elements in a group is another element in a group. Most of the time we'll use the language product. That's just what we usually use, but sometimes it's actually addition, sometimes it might be some kind of fancy division, mod, or something like that. Now the second rule is, the other thing, when I'm stating these axioms, I'm not stating the minimum. I'm just stating what has to be true and what it implies. So I'm going to say right now that the next rule is associative. A, B, C has to equal to A, B, C for all A, B, C, and G. So the associative rule always applies. You might think, well, isn't that true in all of mathematics? And the answer is no. There are things like octonions, which are useful in physics or may have some use in physics, which are actually, they're called non-associative algebras. So this rule doesn't always hold, but it holds for groups and it holds for most mathematical objects. This is the associative rule. Third rule is very simple. Every group has one and only one identity element. You can prove that there's only one. Usually in the axioms they say there exists an identity element, and then you prove that. But I'm not interested in a minimal set of axioms. So there exists, what we usually call it is E. That comes from the German. Same. So there exists an E in G such that AE equal EA equal A for all A in G. So again, you might see some books state only a left identity or a right identity. It doesn't matter. It ends up being both. So there's always a unique element in every group. And for instance, if we were doing some groups under addition, the unique element might be 0. And under multiplication, the unique element might be 1. Okay. There's one other property left. So for every element in the group, there exists another element which we call G inverse, such that G inverse equal G inverse G equals E. So this is the, again, every element has a unique inverse. So these are the 4 rules on groups, and these rules are actually very constraining, especially for finite groups. So I'm going to start by listing some groups of low order, and let's start with, the order of a group, order, is just defined as the number of elements in the group. So for a finite group of order 7 has 7 elements. An infinite group would be said to have infinite order. Order is mostly useful for finite groups. So let's start with say groups. Some don't even consider the group of order 1. Obviously this is just a group with one element. It has a set of E, and you can see that you'll define EE equals E, E inverse equals E, and you'll see everything will hold on the associativity. This anything you do is E. So this is the extremely trivial group. A lot of books don't list that. 2. Groups of 2 elements are usually listed as E, comma, say A. So it's got 2 elements, and a lot of times, especially for small groups, we'll specify a multiplication table. This is going to be very, very trivial. We'll just list, let's call this the 2. We'll have E, A, and we'll have E, A. Okay. And then we're just going to fill in the multiplication group, just like we're in kindergarten. Well, this is the identity element, so the identity element times any element of the group is the same element. So we're always going to get E and A there. Likewise, the identity, any element of the group times the identity element is just going to be that same element, so we're going to get E and A. So the first row in the first column of any group multiplication table always comes out like this. So the only question is, what is this thing? There's only 2 possibilities that it could be. It could be E or it could be A. I'll just write E, A. Now, let's think about what it could be. So what we're going to have is AA, AA. Let's see what happens if AA equals A. Well, we know that there's an inverse element to A, so we can multiply this. AA inverse AA equal A inverse A, using the fourth axiom. Now, using the associative, this becomes A inverse A equals E, because A inverse A by definition is E. Now we get EA equals E, but EA is A, so we get A equals E. You say, okay, what's the problem with that? Well, it's no problem, except that now we only have a group of one element, not two elements. If A is E, we only have one element in the group, and we're back to this case. So AA equals A is not possible. And in fact, AA is equal to E. You get a lot of simple arguments like that. I usually won't run through this. I'm running through them now because it's a start. Okay, that's a two-element group. Every two-element group is like that. Now, you might think that the two-element group is like ridiculously easy and trivial, and it is in a sense, but this occurs in physics a lot. In physics, A is often something like parity. And as I showed last time, we can always break up a function into a symmetric function and an anti-symmetric function using the parity operator. So, because we satisfy, by the way, when I use notation like AA, we'll always write it as A squared equals E. And A cubed, like A is equal to A cubed, and so on. Okay, that's a group of two elements. Nothing peculiar yet. One thing to notice is this group satisfies, if you notice, I did not list a rule that's very common in grade school. In grade school, we have things like AB equals BA. That holds for like real numbers, complex numbers, does not hold for quaternions. And the commutative law does not hold for groups in general. But for small groups, as we'll see, groups with elements 1 through 5, it does hold. So here, EA there's really nothing to do here because we only have A squared equal E, but I'm going to go into 3 elements now. So now we're going to have a set E, A, B. Now here's where I'm going to see if I can get this right and not mess it up. But let's do the multiplication. E, A, B, E, A, B. Let's fill in the first column and the first row. Okay, so what we have to do is we have to fill in these rows in a way that's consistent. And what I want to now claim and show you is that we can never have two elements that are the same in the same row or that are the same in the same column. So let's say, for instance, I tried to put an A here. What's the problem? Well, we have EA equals A, and we have BA equals A. Now if I substitute this over here, I get EA equals BA. And now if you multiply this by B inverse, well, we have what's called multiply it on the right by A inverse, we're going to get E equals B. And we know that, when we list distinct elements of the group, there's only one identity element. So this is one of the important things on group theory and filling out these tables when you first start. We always have different elements in each row and in each column of the group using an argument similar to what I just gave. And not only that, every column is just a rearrangement of the group elements, and every row is a rearrangement of the group elements. So for instance, let's say we're looking over here. I know it can't, let's look over here. I know it can't be A, okay? And it might be B. Let's see what would happen if we tried B. Then we would know that this is E. Then we would know that this is A, because B, and then we would know this is E. So this seems consistent, and you can actually multiply it out and see that this is, let me see if I wrote it down. Probably didn't. Okay. But this is, it turns out there's only one group of 3 elements. If we try to, if I tried to put E over there, let's see what would have happened. Well, there's AE, so then this would have to be B, but that contradicts that. So it cannot be B over there. E cannot be E over there. Can't be A, so it's got to be B. Then this guarantees E, and this guarantees A, and this guarantees E. So this is the group of 3 elements. And one more time, you can see by looking at this group that it's commutative. For instance, AB is E and BA is E. And if you look at any possibility, you'll see that this group is commutative. Now let's go to the 4-element group. And so this group is what's known as a cyclic group. This is a cyclic group of 3 elements. And it's cyclic because we can write the elements as consisting of E, A, and notice that B is just A times A, or A squared. So we can write it as EA, A squared. And when you multiply elements with powers, A times A squared is always going to be A squared times A. They're both A cubed. And the defining characteristic of this group is that A cubed is equal to E. So if we wanted to know what this element squared was, A squared squared is A to the 4th, A to the 4th is A. So that would have been equivalent to saying B squared is A, which is true. Okay, 4th element of, let's do the 4-element groups. So there's actually 2 groups of 4 elements. The first one, usually I think we denote this by C3, and this is C2, and this would be C1. First one is called C4, and this is equal to the set of E, A squared, A cubed, and the defining relationship is A to the 4th equals E. So this is once again a 4-element group. It's commutative. It will obviously satisfy the associative laws, and the inverse, like the inverse of A is A cubed because A to the 4th is E. The inverse of A squared is A squared because A to the 4th is E. So this is one element, and for every integer n, there's a group called Cn, which is just a cyclic group of n elements, and you just label them like E, A to the n minus 1, and you define A to the n equals E. E is in a sense equal to A to the 0. And this is, as I said, this is the cyclic group of n elements. It has some uses here and there, but for the most part, we won't find it that useful. But there's another group of 4 elements. And I want to get this other group. I'm going to call this V, or group has two names. It's called V. It's like the Klein 4 group. Felix Klein was a mathematician in like the 1850s, 60s, 70s, I don't know, somewhere around there. And he did a lot of work on group theory and geometry, called the Klein-Arangler program. So, but it's also called the dihedral group of two symmetries, and we'll talk about that later. But anyway, it's got 4 elements: E, A, B, C, E, A, B, C. I'll fill in. Okay, so let's work on this element. So there's several possibilities here. Offhand, we could say it could be E, A, B, or C. It can't be A because of the column and row restriction. It's got to be E, B, or C. Now, if it's B, I'm not going to go through the whole argument, but it turns out if I make this B, I'm going to get the cyclic group for 4 elements. So you just have to, you can work it out yourself and everything, but what you'll see is if this is B, or it could be C, whichever one it is, and let's say it's B right now, then underneath here I could have E or C. Well, I can't be E because then I would have to have C over here, and that would violate the column rule. So it's got to be C. We can fill out the whole table. C. This has got to be E. Now, again, if this was E, then this column, that would be C. That would violate that row rule. So I have to have C, then I have to have E, and then over here, if this is A, then this is E, and that violates that row, so that can't be A. So we'll get the whole thing filled out. It's got to be E, A, and then this is A, and this is B. Now, offhand, this doesn't look exactly like this, but let's see. We have E. I'm going to have A, and now A squared is B, so I'm going to write A squared equals B, and then I'm going to have A cubed equals C. So let's see if that works out. For instance, A times B, B is A squared, that should be A cubed, which is C. And if you do this, you'll find out that just by renaming the elements, we have the same cyclic C4 group. So by making that choice originally, we got one of the groups of 4 elements, which is C4. Now, let me, I don't need this anymore. Let me work out the other possibility for the 4 group element. This one will really be V or D2. Now, I said before that if we choose B or C here, we're going to end up with the same thing we got before, but there's one other choice. which is A squared is equal to E. And once we do that, this has to be CB. We got BC, but so it's got to be, so that doesn't have the same thing. And then the same thing here, it's got to be CB. And now, I know this is E, but I want to just prove it to myself. If I choose A instead, then this will be E. This will be E. Right, E. This will be A. Okay. If we make this choice, this is another we end up back at the C4 group, where this element is equal to A squared. So we end up getting back, if we go back here, again, there were two E's on the diagonal and two other elements the same. Same thing here. We have two E's and two A's. All we've done is reorder the columns. So in order to get a different group, we have to have E here, A, and E. This is actually, you can verify that it satisfies all the rules. What you really have to verify in these tables is the associative law. It's easy to see that when you have one element in each thing, that we start off, we guarantee the identity. Then by putting one element in each thing, we always have an inverse. So like B inverse, we just have to look where the E is, and it's B. So we're always going to satisfy closure, identity, and inverse. It's not that obvious that we're always going to be good with associativity, and that's what you need to verify. And I'm not going to do it, but it holds. So this is the 4-element group, the second 4-element group. There's two groups of element 4. Let's go to element 5. We'll be stopping soon on this, don't worry. So there's only one group of element 5, and that's C5, the cyclic group of 5 elements. Oops. Not too hard to prove. One thing, there's two theorems which you should know, which is one, well, I haven't talked about subgroups and everything, but if we have a subgroup is like a subset of the groups that's also a group by itself. For instance, if we were to take over here E and A, that's a subgroup of this group. It's kind of like if you just took this, you would get the multiplication group for C2. Over here, same thing, E, A, E. So this is a subgroup. Now one theorem, this is Lagrange, I believe, says that the order of a subgroup, the number of elements in the subgroup, divides the order of the group. So in the case of like a group with 4 elements, we can have a subgroup of 2 elements because 2 divides 4. There's always the subgroup consisting of the identity, and that would be 1, and 1 divides the number of elements in the group. And there's always a subgroup, the trivial subgroup, that's a trivial subgroup with 1 element, and the subgroup with 4 elements is also a trivial subgroup, the whole group. So when we say subgroups, I'm usually excluding the trivial subgroups. In the case of 5 elements, there is no non-trivial subgroup because there's no divisor of 5. 5 is prime. This group is also commutative. And I'll give you one more element of terminology which may come up, probably won't, but may come up. If A to the power K equals E, and k is the smallest integer with this property, then k is said to be the order of the element A. It's another use of the word order. So in this group, a to the 5 equals E. So the order of A is 5. And another theorem which is very related to this is that the order of an element divides, this is the mathematical symbol, I think it's divides the, I'll use the symbol O, the order of the group. So the order of the element A in this group I don't know why, yeah, I guess in this group A squared equals E. So the order of A is equal to 2. And 2 divides the order of the group 4. So we'll always find that now if you would have taken this cyclic group, you say, what's the order of A cubed? Well, to the second power is A to the 6th. And A to the 6th, when you use A to the 5 as E, is going to be equal to A. Then you'll get A squared. Then you'll get A to the 4th. Then you'll get A to the 8th, and so on. You're always going to find that the order of A cubed to the 5 is A to the 15th is going to equal E. So the next element, I'll do this in the next video, we're going to go to groups of order 6. And this is where we'll stop, because this order 6 is the first time we'll encounter what we call a non-abelian group. Non-abelian is just a fancy way of saying non-commutative. Abelian means commutative. Abel was a mathematician. I think I said 18th century. I meant 19th century. Abel lived, I think he died about 1835 or something. But he was actually the first one to prove that certain fifth-degree equations don't have solutions. Galois did it in general and went much further than Abel in the theory of algebraic equations. But both Abel and Galois sort of started on algebraic equations and are considered like the founders of group theory. So all the groups of order 5 or less are commutative groups. And while they have some interest here and there, we'll find that we really want to do non-abelian groups. And what we're going to find is, how do you represent things that are non-abelian? They can't be like numbers because numbers commute. Well, what do you know that doesn't commute? Answer, matrices. So we'll find that we'll get to group representations. We're going to represent groups which are non-abelian by matrices. We can also represent abelian groups by matrices as well, but it's less interesting and they commute. And there's some interesting aspects of it which we'll do. But we really want to get to the non-abelian groups. So in the next video, I'll start with the group of order 6 and I'll start discussing the very important permutation groups. Thank you very much.